And the talk from the University of Manchester, where he started to work very recently. Before that, he was at Imperial College, working with Amy Morgans, well, not with directly, but interacting strongly, I should say, with Amy Morgans. And
yeah, Jusong is not here, so we can mispronounce.
Jusong was at the Beijing conference, if you remember. He was the professor who asked all the questions. We have a nice link here. Anyway, the title of Raphael's lecture is A Combustion Instability Model Accounting for Dynamic Flame Flow Acoustic Interactions. Perfect,
thank you, Maria. So, okay, well, first, thanks for the invitation, because it's quite nice being here in front of you and see this Tango project flourish. Yes, in some sense, my presentation will be in the same sort of idea as the previous one. So, okay, how can we model simple cases of laminar flames and see how acoustic flow and flames are acting together. So let's start now with a quick introduction. So we've seen that, but it's always good to remember everyone. So combustion instabilities, they occur in lots of different types of industrial configuration, and they can have some problem, vibration structural fatigue. So this one maybe some people may not agree, but in my cases I can see stuff like this happen. And here, as we saw earlier, some pictures. So here you can see some damages that have been obtained from the bad effect of combustion instabilities on parts of combustors. And talking with people in industry, combustion instabilities is still a very active worry for these people. So we'll discuss briefly what happens. So we have large amplitude fluctuation between pressure and flames that grow in time. In some sense, that's what I mean by self-sustained. They sustain each other, generally around the characteristic frequency of your combustor. So again, I think we've got more or less exactly the same wording here. The objective is try to understand how these instabilities occur and what's maybe the physics or the mathematics behind it. Yeah? So just the physics of combustion instability as I think I understand it. So there's a few different processes. So one that we've heard a lot about so far is that the flame excites acoustic pressure excites the flame, etc. And if the two unsteady heat release acoustic pressure in phase, then we've got a growth, and that's this Rayleigh criterion that we've discussed. But some other sort of physical aspects that we've discussed a bit less are that, acoustic velocity and acoustic acceleration. Here acceleration is quite important. That's what I mean by dynamic in the model, is that the acoustic acceleration also would have an effect on flame front, which itself will have an effect on the acoustic pressure. And the flame and the surrounding flow are also interacting together. So when the flame shape changes, the flow locally changes. Well, you've got density jumps that depend on, say, the heat release, and the hydrodynamic also modulates the flame front. So we've got this sort of system of three-way coupling that I call between flame flow and acoustics. And the length scales of different processes here are very different. So we've got something, because it's intrinsically multi-scale, can become very challenging in terms of direct numerical simulations, for example. So hence the interest of low order or mathematical modeling. Okay? So I just There may be a crude approximation, but the way I see the world of mathematical modeling and combustion is sort of divides in two parts when we're thinking of flame description. So one is the G equation that we've discussed a lot today, and in some sense here I have a slide on that after, and I'll precise what I mean here. By no hydrodynamics, so we've seen a case previously where there's the flow was modeled, but in some sense the fluid in the G equation flow has to be imposed from somewhere. So we have to say it's coming somewhere. It's not coupled with the rest, right? So that's what I mean by no hydrodynamic interaction. And the dynamic effect of the acoustic that I've talked about is not present. So the acoustic acceleration. Right? So this is one part, and the second part is something that is called hydrodynamic theory of flames. So this model, so based on asymptotic formulation that try to describe the interactions between flames and flow. Okay? And so these two papers here were published in the same year, in the same journal, in the same version of the journal, so exactly the same time, and the two are father of this theory here. One thing in that theory that is not here, is that in this case it's flame flow interaction. So acoustics, there is nothing about acoustics here. And okay, I will present this equation a bit later. Under certain assumptions, we can reduce it to an equation that I call Michelson-Sivashinsky that I will present a bit later. Okay. My idea, and Zusong's idea as well, is to try now to have a model that, keep the advantages of each of them, but also it's sort of a mixture between these two. And also started from first principle, try to be as less empirical as possible. And to have explicitly this acoustic flame flow interaction built into the model. So some of the theory here originated in that paper, and then very recently we developed the theory a bit further and implemented it into a simple way into this paper. Well, yeah, it's just been accepted, so it's not yet available, but I can send it to you if you want. And what I will talk about today is mainly a description of what's in there. Right, so in some sense, that's what I like to achieve. So J equation is good at advection, velocity advection of the flame. Flame acoustic coupling is good. RT here stands for Rayleigh-Taylor effect, so that's what I mean by the acoustic acceleration modulating the flame. And here, hydrodynamics coupling, DL here, is something that is called Darius-Landau instability. You may have heard of it. So Darius-Landau instability is basically the fact that if you take an unconfined flame that is flat, the flame will have tendency to curve and stretch to cusp versions, probably a bit what you mentioned here. And in order for this to happen, you need to have the coupling with the surrounding hydrodynamic. The Michelson-Sivashinsky equation, hydrodynamic theory of flame, so you can have advection, so Darius-Landau instability is included in these models. But okay, there's no acoustic flame interaction and dynamic even less. Okay. So the aim is to have something that has all these points together. Right. So just briefly, I know it's probably not necessary now because we've just heard for a long time about it. So G equation, I write it this way. I've noticed that we've got a sign difference in front of the burning velocity, so I'm not exactly sure. Well, probably the choice of normal or something like this. So that's a level set formulation, have we heard? So that's the burning velocity. And generally, so as a first, something that is done is to write, okay, G x minus f. So you lose the level set formulation, you assume, as we see, it has some drawbacks. That's what we've heard at the last talk. And consider generally also, this is very this is a formulation that's very much used in engineering, where you also consider that you have one-dimensional longitudinal velocity. That is, if you wish, the acoustic velocity arriving on the flame, if you consider 1D acoustics. And then you've got this square root here nonlinearity. Right, so this is used a lot in this kind of configuration when you've got attached flame, because if you think about it, if your flame is attached here, and you bring a one-dimensional perturbation to it, you can still wrinkle your flame, right? Because of the attachment there. So UG here, generally stands for the people call it U gutter for some reason, and that's more or less the velocity at that point there, at the point of attachment. Okay, but this framework here, for example, in freely propagating flame, then you can't wrinkle your flame. If you impose 1D acoustic to a freely propagating flame in purely advection way, it would just do that. It will never wrinkle, right? Okay. So that's a brief, probably too brief summary on the G question, but thankfully we had a lot on this. The Mikasen-Siwashinsky equation that I've talked about a bit earlier is a reduction of the aerodynamic theory of flame. Where phi represents your flame shapes, and gamma here is not the gamma that you are used to. So don't think of it as 1.4. It's a free parameter. I will make it less free in a minute or 10 minutes. But in some sense, it's for those that like mathematics, it's a Hopf bifurcation parameter. So. And here, this operator I here is defined like this. If you take the Fourier transform of it, you got mod k times the Fourier transform of your flame. So this is Fourier transform. In that case, I wrote it in 2D, so in the y direction. If you imagine a tube, the x direction is that one, the y direction is that one. Okay. And so this I is also known as Hilbert transform. Okay. Right. So this is good for unconfined, freely propagating flame, okay? Because if you're confined, you've got acoustics. And that is good at predicting Darius lambda instability, and in particular at predicting high wave number cutoff, because that's the problem when Darius lambda talked about this first instability. It was shown to be unstable for all wave number. But in this case, there is the cutoff that we expect. Okay. Right. Okay. Now I want to talk to you about a very interesting and simple experiment. That's probably why it's so interesting. So you have here. So this is done by Jeff Survey in Marseille, published in '92. So you have a tube here. Now it's roughly 1.2 meter high and 10 centimeter wide. I think that's what it is. You fill it with a mixture of fuel and air. I think in this case that's propane. You have a pressure sensor here. You ignite the flame there. What will happen is that the fuel will be consumed and the flame will propagate downwards till no fuel is left. Okay. And what's very interesting, so this is that it's got this type of results. So here we're showing pressure fluctuations here, right? So your flame goes down, it starts being curved. It's curved, and here you've got this is the mean flame position in the tube. So when we are around 0 there, it means that we are at the top of the tube. When we reach 1 up there, it means we are at the bottom of the tube. Okay? And then this axis is the acoustic pressure values. So the flame is curved. You have a first exponential growth followed by a saturation of pressure. Okay, we are familiar with this. It looks a bit like the famous limit cycle that we talked about a lot. And then when the pressure saturates, this profile here flattens. So will be like this, okay? And it propagates at constant speed, and that speed is what we call laminar flame speed, okay? So the speed at which a flat flame propagates. And then this flame profile remains flat till the very end, okay? And the pressure remains saturated. Okay. So that's an interesting result, but there's an even more interesting one, is that if you change slightly the value of your flame speed, so if you change your equivalence ratio or something like this, then you can get something like this. Right. So what happens here? Same, we start curve, first exponential growth, saturation, the flame becomes flat, and at some stage, we've got a huge, violent instability that starts from the limit cycle. That is indeed not the limit cycle like this, because it doesn't remain further. And at which case, the profile of your flame starts to become cellular, so you can see small sort of oscillation, wrinkling of the flame. So generally, what we say is that this part here is what we call primary instability, and this one is a secondary instability. Okay. So the aim is to, and in some sense, it's possible to show that such behavior in acoustic flame relationship, you can obtain something like this with the G equation, right? This thing you can't. If you start now from an established acoustic field given, and you look at the hydrodynamic theory of flame, you can get something there, but you will never get the first one. Okay, so the idea is to try to see if we can obtain a sequence of instabilities like these with a simple model. Okay, so for those interested, I'll go quickly on this, but there's been some work on flame flow acoustic in the literature, obviously, loads on externally imposed acoustic on the flame. So that doesn't consider, say, back action of the flame onto the acoustic. And that's generally, that's what I was saying, focused on the triggering of this secondary instability. And there's one important work that is that one that was sort of the first one to try to consider what I call spontaneous acoustic field. So you don't send any acoustic into your system, your flame itself will generate some acoustics. And this acoustic will grow to some threshold that will lead your flame to become unstable. Okay. And so here this was focused on the primary instability, and was made with some sort of simplification regarding the flame profile. Okay, but that's in some sense this paper has been very inspirational. Right. Okay, so now that's more or less it. We're going to start doing some modeling. Okay, so that's the problem I will be considering. So you have a long tube. In that case, I will say close at that end, open at that one. And a typical configuration is when you have, once you ignite your mixture, then you will have something like this. Okay, a flame profile in the middle, separating an unburnt and a burnt region. So here, for simplicity, then this can hopefully be changed as well. Here, I will not see. I make this assumption. Okay, so that's not going to be a level set formulation, right? I said that. And here, but that can be 3D in some sense. Yeah, I can have Y and Z, etc. And other assumptions are assumptions of periodicity there. Okay. Right. In terms of physics, we're going to do some mathematics here. So if I consider 120 chemical reactions, that becomes problematic. Plus so that's going to be one step below a chemical reaction. Fuel plus air gives heat, roughly. Sebastian mentioned earlier as well, I think lean combustion is something that's interesting to look at, because it seems manufacturer, in order to save nitrogen oxide emissions, they found that running combustors in lean case was quite good. But what tends to happen is that combustion instabilities happen more often in these situations. Right, I will assume that I've got a perfect gas state equation and that we consider a compressible fluid. Right. The equations that we look at, the entire sort of set of equations, so you need, again, we've seen some of them with Maria yesterday. So you need the conservation of mass, conservation of momentum, so your typical Navier-Stokes equation. You need another equation that we didn't talk about too much yesterday. It's transfer equation for chemical species. Okay? Energy conservation, we talked about that. And the state equation to close your system. Okay, so in terms of notations, so these are quite standard. Theta is the temperature, and the subscript minus infinity means fresh mixture. So what happens before we even burn anything in the tube. UN is the laminar flame speed that I talked about, and that was called SL, I think, in Sebastian's work. Here I will consider Mach number, so Mach number is M, and I have to stress here that the Mach number, contrary to other situations, especially in engineering or in attached flame, is not defined with respect to an incoming mean flow, but is defined with respect to the laminar flame speed. Okay? Because whatever happens, this will always have a value. Right? If you stop your mean flow, in your case, your flame is still burning, but then your Mach number is okay. Is zero, but you can still have acoustic. So that's the idea behind that. Delta here is a parameter that characterizes flame thickness. So that's going to need to be small. I'm going to explain a bit more about this. Q, alright, heat release here. I mean mean heat release. So you can compute it from the ratio of the temperature before and after the flame, okay, if you know them, which I found is not very easy to measure experimentally. And finally, two more parameters, beta, activation energy. So how much energy do I need to put into my system for the reaction to start occurring, for the combustion to start? Okay, so it's also called, it's not exactly the activation energy, it's what we call Zeldovich number. And finally, NA here is the Markstein number. So, Markstein number is a number that characterizes the effect of flame curvature on flame speed. So, how the stretch of your flame will change its burning velocity. Put simply. And it's some... Okay, now I will stop there. Right, so the first thing that you need to do, if you start, you've got the geometry that I showed earlier with color, it's exactly the same thing. I've not dimensionalized, so this is 2 pi and this is a certain distance, it doesn't matter. But in order to do some work, I want to be in plane frame of reference. So I've got my f defined here, and I just change some variables. So I go from x, y, z, t to psi, eta, z, tau, where psi is this x minus f. So if you want, if this formulation is correct, psi will be your g in the g equation, but this assumption here stops from the levels of formulation. And then eta, zeta, tau, they remain y, z, t. Okay, and if you do that, then your geometry pass from this case to solve that case, where your flame is a flat line at psi equals 0, separating unburnt and burnt mixture. Right, so just a few notations. So I will separate my velocity between longitudinal and transverse velocity. And I will use this nabla tilde for describing the reduced gradient. So that's the gradient just in the transverse directions, eta and zeta. Right. Okay, so one way of tackling this type of problems is asymptotic analysis. So we will need to make some assumptions. So typically, that's how hydrodynamic theory of flames works. You assume a large activation energy, so you need to input a lot of energy into your system in order for it to kick in. And we assume that our flame is thin. Okay? And if you do that, then you can have different length scales. So one above the delta beta that we call reaction zone, that's when chemistry occurs. So this is very thin. We've got a one-step reaction. Well, chemical reaction occur very locally. Then above the delta, you have the preheat zone. So that's where temperature diffusion is important in the system. And above the one, okay, you have the hydrodynamic flow, I consider about the one here. And so this, in some sense, this subsystem here is the hydrodynamic theory of flame. And what's very nice in hydrodynamic theory of flame is that these two zones, so the reaction and the preheat zone, can be tackled analytically for one-step chemical reaction. And so, and then the result of this is that you kind of know some jumps across this interface for your hydrodynamic flow. Okay. And then, what's interesting is if your tube is long enough, then you see the appearance of an acoustic zone that this time will be over the 1 over m. So m, we assume low Mach number, 1 over m is big, so far away in the tube, we've got a zone where acoustics changes, okay? And then, so this zone here is small compared to the acoustic length, and so you can get jumps of acoustic across this whole region, right? Okay. So, in order to get to the acoustics, so we start from a whole set of equations that I did not write here on purpose. And you make this simple change of variable. So you stretch your variable psi, or right inside tilde is m psi. And if you do that, out of your whole system of 5 big equations, come out naturally, though not easily, but you have to define this PA. It comes out acoustic velocity and pressure that can be shown to satisfy these equations. Here, there are simple acoustic equation. One thing that I want to stress here is this R here, which is the density to leading order, say in the flame thickness, and in fact, for the density it's to every order in the flame thickness, but it's a detail. But what's important is R is constant on each side of the flame, but the constant is different. There is a density jump across the flame, right? So R, so this equation, so if you want, if you're on the unburned region, R has a value. If you're in the burned region, it's got a different value. Okay, and this value can actually be computed exactly in terms of the mean heat release. But what you can also, so more importantly, so this, in some sense, we could have posed that, say, oh, acoustic propagation does this. Okay, what's interesting? First, it comes out of the whole equations. Second, you can derive analytically the value of the acoustic velocity jump across the hydrodynamic zone. Okay, so here I have put it to leading order in delta. So the jump of acoustic velocity can be given in terms of F, with F represent the flame shape. Okay? So, and what's interesting in the theory is that J actually we know it. First here I've made a simplification that I talk about, like a weakly nonlinear. In fact, you should get a square root of something there, but then you assume that square root of 1 plus x is x divided by 2 for small x. Okay, so
what is F again?
F, okay. Yeah, F is the flame shape.
Okay.
Okay, so you get your jump in terms of the flame shape here to leading order. In some sense, this is related to the film proportionality between flame area and source of right. And we can go a bit higher in delta, but I'm not showing it here. But that's very interesting because we've got here acoustic jump, flame shape, acoustic flame coupling here in the acoustic equations. Right. So this, in some senses, the calculation of this comes from the mathematics. It comes naturally. Right. So now we want to know what happens in hydrodynamic zone. So hydrodynamic zone, here I put everything to second order in delta, but so you can, okay, if you linearize the hydrodynamic equations, you obtain something like this. Again, I remind you that R here is different on each side of the flame. So you've got linear equation, but you've got jump in density on each side of the flame. This is the Prandtl number, so you can take into account viscosity terms. So you've got this, and from I've mentioned to you earlier to tackle the reaction sheet and diffusion zone analytically, you can express the jump of your hydrodynamic quantities in terms of other variables of the system. And this GU, GV, GP can be written explicitly, but it doesn't fit on that page. But you can write it explicitly. And here, that's something that I did not mention. This BA here term, so the jump of acoustic pressure depends on this stuff there, which is given as, if you wish, the jump of the acoustic acceleration across your hydrodynamic zone. Okay. I will come back to that a bit later. When I use minus, it means the velocity field just before the flame. And another thing that comes out is a flame equation, okay, that has this form. So in some sense looks similar to the G equation, right? So you've got your derivative, then you've got your hydrodynamic field here, your gradient, your square root. And here you've got in delta that is responsible for cusping in shape and also to give the cutoff of the large wave number for disolar instability. And here you've got another term, okay, that again I can write down explicitly. But what's interesting is this, we can see that here in this hydrodynamic system we've got acoustic flow coupling because the hydrodynamic variables are linked to the acoustic via this term, and flame flow coupling because the green things here represent the flame and link to the flow, and here the flow is inside the flame equation. Right, so between this acoustic that we saw before and this hydrodynamic now, we've got the three-way coupling appearing in front of us so explicitly. Right, so for the purpose, there's one thing here. This term here, for the purpose of this talk, I will simplify it to this, by this, like a weakly nonlinear assumption. Okay? This is 1 plus grad f over 2, grad f squared over 2, and this is because I want to make some connection with other equations. Right, okay, so we assume that the gradient of the flame squared is reasonably small, which is not a terrible assumption. But if we want, we can keep the square roots. It's just
Is this from Taylor series expansion?
Yeah, this is for Taylor series expansion of this stuff as when this is small, just simple. Right, so now what I want to stress is for today, we'll make a bit more simplifications here. Because, okay, that's not just now. Okay, what now? So the whole system that is just seen, if you use Fourier analysis, so you Fourier transform in the transverse direction, you can reduce it drastically. I will explain how. The other thing is, if you assume some simplification, physical simplification, the model that I showed you can be reduced in some cases to the G equation, in some other to the Michelson-Sivashinsky equation. But for today, the objective will be to retain key terms, allowing for simple model, because I believe that now you don't think this is simple, accounting for this three-way coupling. Okay? So in order to do that, I will get the first system and consider only leading order terms. Right, so you have the dynamic equation simplify. You don't have viscous term anymore. Which, by the way, for some of you that are interested in this thing, even in the case of higher order in delta, where the Prandtl number is present, the Prandtl number disappears totally from the equations once you reduce it to lower order model. It doesn't seem to have an effect at all, even to first order in delta. But okay. This is a detail. And then now I can, it fits on the slide. So to leading order, I can write explicitly the values of my jumps, hydrodynamic jumps, in terms of the flame shape and the back action of the acoustic here. This is a term representing gravity, okay? This is a, we can include gravity in it, that's not a problem. Again, so this is the back action. And the flame equation, we will simplify it to this. So you notice I drop off the V dot grad at the moment. And this is the only term in delta that I keep in it. And the reason why I keep that term is what I've explained to you, to allow to get cusp and to have this diamond outcome. Right, and again, here we get our coupling. So acoustic flow, flame here. Okay? Right, so what can we do with that? It turns out that we can simplify this a lot, as I was explaining to you. So, but first, I want to do something, is to look at the steady states of this system. Okay, so steady state, acoustic, we don't consider acoustic. Acoustic is an unsteady process. So if I look this stuff and roughly I drop off the time derivative, what do I get? And it turns out that the steady solution of the system I've just shown you is exactly the same as the steady solution of the Michelson-Szymanski equation. Right? And these three parameters gamma that I've talked about can be related to our physical quantity like this, Q over delta times the Markstein number. Right. And, okay, I've not been, I computed this steady state reasonably quickly in a Fourier series framework. But what's interesting is in some cases, this paper is a very nice paper where they describe all the steady states of the Michelson-Szymanski equation, and in some cases they give analytical results. So I say, okay, let's compare with the analytical result. And here is for gamma 2.1. So this is the red dot are the numerical results, and the one pole solution is here. Okay? So that's the analytical in blue, the red in numerical. And here, again, for gamma 6.2, that's a bit different because there are two steady states to the Michelson-Szymanski equation. One pole solution and two pole solution. And it says that my numerics capture the two pole solution. Okay? That will be very important in a minute. Okay, but the main results of this paper, there actually are two papers, one after the other, is that they tested for the stability of the steady states of the Michelson-Szymanski equation. And here you see what I mean by gamma being a bifurcation parameter. When gamma increases, this equation has more and more steady states. However, in the framework of Michelson-Szymanski equation, so in the framework of hydrodynamic theory of flames, can be shown that they're all unstable apart from one each time. And that's always the one associated with the most number of poles. Okay, let's just, the number of poles is just a way to give a name. We're not going to enter into the details of that, but it's just, okay, so either one pole solution, two pole solution, and that's who we're in that case, okay? So in some sense here we capture numerically the stable steady states, and here as well. Right. And if you switch on the acoustic and you use a linear stability analysis, so we talked a bit about linear stability analysis yesterday. If you do that, you can find that indeed, actually all these hydrodynamically stable steady states are unstable when you switch on the acoustic. So I explained that graph briefly. So here is you have your growth rate, and here sigma. Okay. We assume that you can, for computational purposes, that you can keep the mean position of your flame in your tube roughly constant. Okay, you can say by feeding it, let's say we're feeding a mean flow that is equal to the burning velocity, then your flame will remain roughly located, can remain roughly located at a position. So sigma is that position. For example, sigma is 0.5, it means that we leave the flame roughly in the middle of the tube. For each mean position that we decide, we can compute the maximum growth rate seen, and any position is actually unstable. Right? So, and this is obtained purely analytically. Well, apart from finding the eigenvalues of a smallish matrix. Okay, but this, I was a bit worried because I got these results, I say I don't want to be in bad terms with these people by telling them. Okay, so in some sense, then I wanted to do some more numerical investigation of this problem to see if this was right. And this, we'll talk about this one equation model. So you take the whole hydrodynamic system and you use, as I told you earlier, Fourier analysis. So in a times zeta direction, so you can do Fourier transforms. And the whole hydrodynamic equations, hydrodynamic jumps and flame equations can all be reduced to one equation in that case. And this equation looks like this. So f hat is the Fourier transform in the transverse direction of your flame. A, B, and C are coefficients that we know explicitly in terms of the parameters of the problem and the wave number and this little term here. And what we've got on the right hand side comes from the quadratic nonlinearity, where, so this is the convolution, so if you take the Fourier transform of a square, you get a convolution. Right? Okay. And again, this we know. Exactly. So now if I look back, my whole problem is reduced to this equation and to the acoustic system that I've described earlier with simple equations, just, you know, a hyperbolic equation. Right. So let's try to see what we can do numerically to try to confirm stability results. So acoustic resolution, you just got your system here. The problem is that you've got discontinuity across the flame of, say, your here, and you've got boundary conditions. We've discussed it a lot with Cameo. So okay, open end, close end. Okay, that results into this. And here we have a jump across the interface. This jump, J of t. For this slide, I assume that I know J of t for all time. And then this whole system, we discussed this yesterday, in maybe for a more complicated structure, but I mean, this can be solved analytically. This is method of characteristics. So you sum of backward, forward propagating flames. So we've heard a lot about this. Okay. So in theory, if I know this term for all time, then I solve this easily, even in almost zero time. Yeah. Right. So what about the other thing? So I have my big equation there. I can consider it as an initial value problem. So I need an initial profile. Let's take this initial profile as a small perturbation of some of the steady states we've seen before. So for the value of gamma, we have the steady states. I perturb it slightly. This, I make this assumption because, well, I need to make something. Assume that it's. And the convolution can be evaluated by fast Fourier transform. And we can march in time in this equation. We can march in time using any scheme. The restriction of the following, the schemes will have to be explicit. Okay. So, but here, I assume again that I knew BA for all time. So if I know this, then I can solve my flame equation. And the problem, I know neither JA, neither BA. So the idea is this sort of coupling diagram in combustion instabilities, if you want. I think they had something very similar. So you have to have a sort of hydrodynamic / flame solver here, like a spectral flame solver, and an acoustic solver that takes into account the acoustic propagation. So at each time step, I solve this. This gives me F, the flame shape. From this, I can compute the jump, the acoustic jump, across the interface, right? And I fix that into acoustic solver, then analytically I can obtain the acoustic acceleration across the interface. that then I feed again, and each time step I rotate like this, right? Okay, now let's see, enough theory for the moment, sorry if this was a bit too much. Let's see what happens. Okay, so I just want, the problems I consider, as told you, so I remain, I said, for now I remain centered roughly in the mid position middle of the tube. Mach number, all these parameters are the same as in Serbi experiment, at the moment apart from this one. I don't consider gravity in that case. Let's imagine your tube is horizontal. And I present results for different values of gamma. So the one that are corresponding to the nice steady states that we found, etc. Okay, gamma 2.1. I compute the acoustic pressure at the closed end of the tube. And I do get something like an exponential growth followed by saturation or limit cycle. Right? And if I look meanwhile at the flame shape, what happens? I start from a perturbed steady state. When this grows, there is a tendency to flatten. So it goes down. Once this limit cycle is established, my flame is flat and remains flat for all time. If I continue my computation forever, it will stay like this. Okay, what happens is gamma is 6.2. Gamma is 6.2, similar beginning, first exponential growth, saturation, and then I've got a big thing that kicks in there. That I can't compute for very long because it's very, very strong, this instability. Okay, so if I look at the flame shape, I start from my initial steady state slightly better. As the exponential growth occurs here, my system flattens, gets almost a flat state, and as this starts to decay, I've got some wrinkling starting to appear. So the flame becomes cellular. So it's kind of some behavior that were presented earlier. Okay? It looks a bit similar thing than in the experiment. But still needs validation. So the good thing in here, it's pretty easy from this graph to calculate the growth rate of my first instability. Okay, and in fact, if I compare it with my analytical work, then these points are numerical evaluation of the growth rate by measuring on the graph, taking the log or something and fitting a straight line. The different colors means I perturb the steady state in a different way, but it's not very important. Forget about this. And same in this case. Well, okay, so at that stage, what do I know? I know that my instability result is probably correct, but nothing else. Okay, I've got the growth rate, but well, linear stability analysis can't tell you anything about what happens, even not the plateau level, nothing. Okay, but at least we've got this. Right. Validation 2. For nonlinear behavior, here is a plot, say, of the back action term. It looks pretty much like the acoustic pressure, but the amplitude is different. Okay, and then the same in the case gamma 6.2. Say, I take the Fourier transform in time, this time of this stuff. I can show that there is one dominant frequency in these two cases. Well, you can see it very well here. And it turns out that this dominant frequency is the first characteristic frequency of my dot. Okay, I call omega 1. It's dominant. I've got pressure saturation. Okay, so once I'm here, it's not a bad idea. We've seen that. I mean, Maria did some stuff before, but once I'm here, I'm already there. Okay, if this looks like a cosine times a certain amplitude. Okay, I can try to estimate my amplitude here between 130 and 150, here between 430 450, say. Okay. And what else do I know? I know that when I saturate, my flame becomes flat. So I can try to linearize my whole spectral flame equation around using this and linearize around the flat state. And if you do that, it can be rewritten like this. Change into what is called a Damp-Mathieu equation. And Damp-Mathieu equations are very nice because it's possible to study the stability of solution of this equation rather easily. It's called Floquet theory. Okay. And so, what you can do is draw stability maps. So, here is the stability map for gamma is 2.1. So I've got a zone of instability here, and the word rate is stable. And if I put my amplitude estimate there, and if I look at my node, so remember we've got something periodic, so in our case, and that was 2 pi the distance, so in our case we're only interested in integer values of k. And so all the integer values of k are in the stable region. So my flat state, for this particular value of gamma is stable, okay, which is what we see. Right, same stability map for a different value of gamma. In this case, you've got the first instability region, and then the second instability region here. And if I put the amplitude estimates that I had, and I look at the value of my case, it turns out that two of them are within the gray area. And in fact, 5 is the number of oscillation that you saw in the wrinkling of the plane. Okay, that's no like it's for this reason. And we can even say a bit more about this instability here. And this instability is called parametric because it comes from the amplitude times the cosine thing. And we can say that it's subharmonic instability as well. The reason for that is the following. If you imagine your system, you've got your acoustic, right? You've got your flame that wrinkles. The wrinkle oscillates in time like this. The acoustic oscillates in time. And if you plot the two oscillations next to each other, you see that the period of oscillation in time of your flame is twice the period of your acoustic. That's what we call by subharmonic. So the frequency of flame oscillation is half that of the acoustic. So when I don't know if there is a pen there. Oh well. Anyway, so yeah, if I've got six oscillation in the acoustic stir over a period of time, I would get only 3 in the flame. Okay. Right. Okay, what can we say now? Physical interpretation. So that curved steady state, despite being predicted to be stable by hydrodynamic theory of flame, when you incorporate acoustics, so you confine your flame, then they're actually linearly unstable. In some cases, a flat flame that by Dirichlet instability is intrinsically unstable can survive and stabilize itself with its own noise. So the noise that the flame creates helps stabilizing it. Okay? In some other work, you can see that some such flame can be stabilized by external acoustic on it. In some sense, but in other cases, if you go a bit higher, then you've got different type of instability. You've got this subharmonic parametric instability that kicks in, and it's very strong. Okay, so we've got here reasonably qualitative correspondence between the experiments and this. Okay, so now let's try to be as close as possible. So let's consider the flame not at a fixed sigma position, but sigma can be computed with time. And we consider gravity, and we try to be in the same configuration as Serbi. Okay. And here, what we start, in my case the difference is I start from a flat front because I didn't know what to start from. Here this curve state at the beginning of initial happen. But what happens is soon the flame starts to curve. It curves. Pressure increase, flame flattens, propagates longitude flat to the end. Okay? In this second thing, what I had, I start flat for the same reason. Curves, exponential growth, flattens, propagates flat, becomes cellular. Everything is, no, that's thanks. Okay. So here the axes are the same. So I could almost pretend that it's a quantitative agreement, but I will tell you why it's not. All the parameters that I've used are the same at the experiment, apart from one. And that one is the one that has been important through this presentation, is the gamma. the value of the gamma. Turns out that if I extrapolate the value of gamma from the experiment, it's much, much higher than the value of gamma I use. Okay, so I stick with qualitative agreement at the moment for this reason. Okay, I will change this. Okay, yeah. Something I wanted to talk about, I think we've had a little bit of vorticity, vertical things, is that my equation, imagine I have a very big forcing of the hydrodynamic field. If I do that, the equation doesn't change, there's just one term that's added at the end. Now again, it's explicit in terms of frequency of the disturbance, wave number of the disturbance, because so what happens is that you will take your U and you make it change like this, right? And this oscillating time. That's what I mean by vertical disturbance. And epsilon is the amplitude of the disturbance. And what's interesting here, I look at what happens in the case that the flame was stable in its own, I guess the flame is neutral, in its own acoustic field. So epsilon is 0 is exactly what I've shown you earlier, when you've got exponential growth followed by saturation. And then you start playing with your field, or modeling some sort of weak turbulence or something like this with these vertical disturbances. And that seems to trigger yet another type of instability after. And then here you can see the evolution of this is just the envelope of the acoustic pressure for different values of the amplitude. And if I look at the flame shape, so this is the case epsilon equals 0 that I've shown you earlier, but just put it in a different way. Up to the steady state, your flame tends to flatten, remains flat then for all time. And 0.6, so it's here, same, start from a steady state, gets almost flat, they start to see some wrinkling, and then they start to wrinkle again. Okay. So that's a different way of triggering something I was saying. Do I have time or not? Okay. So this is not my specialty, but I just wanted to stress that the model is compatible with feedback control. So imagine you've got something like this. So you can measure your acoustic pressure somewhere. You got a loudspeaker in front, and you link the two together. By this typical model of control theory, okay, so you got the open plane, the cross correction, etc. And if you choose your controller, here I'm going to do something that's called adaptive control, so self-tuned regulator algorithm. If you choose a controller like this, so for those that do control theory, they should say very weird, because S, okay, is the Laplace variable, so okay, so S and T generally they don't appear in the same equation, right? Either way in the Laplace space or in the physical space. But here it's just a normal controller of which allows some constant to change slightly with time to adapt to the situation. Okay, and you can actually write down the update rules of these two parameters, nothing to do with the gamma, I'm afraid, are how fast you want your control to work in some sense, and that can be quite sensitive to that. Case without vertical disturbances. At the black line here, so first, in dashed line is the envelope of the case that was the stable flat flame, limit cycle, etc. At the black line, I switched on my control algorithm. And you see the evolution of the constant here with time. So one is almost not moving, the other one is stabilizing to a different value. And here the amplitude is kind of killed. Okay. But it seems to work for a more complicated case. The vertical disturbances, so we saw for epsilon 0.4 that the envelope is very high, massively with another type of instability. I apply control here again, that seems to stabilize the whole thing. Okay. And in the worst case scenario, epsilon is 1, but still seems to work. Right. But some, okay, I had some criticism because this is not killed. Okay, but this is, compared to that one, so that's quite better, right? And so I tried to play a bit with this, and I can come up with a strategy. I'm not sure how good it is, but it seems to work. So try to kill the signal in these cases. So the idea was to change, because at first, for this to work, the parameter of the speed of the control is very sensitive. You need to choose them to be very low. And then here what I did is, okay, once we're in a self-established region, well, maybe I can increase the value of these parameters. So what I do is that each time we become calm, I multiply them by 10. And in fact what happens is that, so here you had for epsilon is equal 1, here you had without control. In orange you had one control applied at the black line. And at each pink lines here, I multiply the control parameter by 10 and I seem to kill the pressure. One issue here is that the value here don't seem to converge to a fixed value as good as before. But I'd like to see, in some sense, if we could do that experimentally. Right. Okay, so I'm there. Summary, when it comes to, so this is flame model flame. So by complete flame model, I mean consider the three main physics interactions that I was interested in. There are others. There are other mechanisms that lead to instability that you mentioned, variance of equivalence ratio. So this is not taken into account here. Then looked at this simple model, linear stability analysis, and it was sort of confirmed with a numerical scheme. But so something I did not mention, for example, the numerical case to get the limit cycle and the flame flat it's on one computer for 5 minutes maybe. So it's not very expensive in terms of other things that have been done. I've talked a bit about here. So with turbulence. So this is a conference paper, so it has not yet been published in real journal. Adaptive feedback control, and this I didn't talk too much about it today, but we can go higher. My hope is to get better quantitative agreement by going higher in the synthetic description. Okay? So what needs to be done, as I was saying here, maybe refining to get better quantitative agreement. And my weak nonlinear assumption can be released. That's not a problem. I just need the time. Right? It runs, but I don't know if I should trust my results yet. Okay? Because that's the big thing with what I made, is that I could compare my results to some really mathematically established things. When I start to release this assumption, I got some stuff that look nice, but I have no idea if it's correct or not, so I need to. And then maybe this. I was thinking there could be another way to, if you do acoustic loss in the system, then I will probably stabilize the system and I can go higher in gamma in some sense to match the experiments. Okay, right, that's it. Well, thank you very much for your attention. Yeah.
So the flame equation,
Yes.
does it have any bound conditions?
Well, periodic boundary conditions.
You can imply something else.
Sorry?
You can put something else like volts or I don't know.
Well, you can. So something I don't mention here is that we're trying to do the same work for attached flame. So for attached flame, say, it can be done, but the advantage that we get here by going in the Fourier space is a bit lost in the attached flame, because imposing boundary conditions that are physical on stuff that you go into the Fourier space, you need to do some extra work, like to get rid of Gibbs phenomena and this kind of things. It can be done, but it's not as fast, let's say, because it's not suited. Like, but this problem is exactly suited for this. It's periodic. It's freely propagating. Yeah. So that's how that answers. Yeah.
You have some information on if you would include heat losses due to radiation or that you remove it from the flame?
So,
Stabilize more or?
well, in some sense, I mean, it depends what you mean by heat losses for the flame. Because here, in some sense, there's something that's supposed to be exact. You know, I mean, the heat losses from the walls, that's different. Because the walls are adiabatic. Yeah, maybe this. But from the flame itself, I mean, I get the source term, it comes in from the equations. But, yeah.
I was thinking if you have because heat is also radiated away in this. I think some experiments is also really important parameter for this stabilization or.
Well, a typical thing that you see is imagine I've got my flame here. Experimentally, mathematically, that's something you see. Okay, that's the temperature profile. So, I don't know what you mean by.
We see the whole gas will radiate energy away. Yeah.
This is the whole gas, yes.
Yeah, then that would be more.
Well, but okay, if you look at density, then you get something like this. But I mean, I don't know, because here it's taken into account that in some stage the temperature change, density jump. It is maybe I don't really understand.
I mean, the constant is not the temperature is not constant.
Here.
Yeah, and that. Yeah.
Okay. Yeah. So no, this I assume that outside this zone the temperature is constant.
Okay.
And maybe, and it seems to be the case for one-step chemical reaction. Then, complicated chemistry for this type of things. Some people are trying to do with 2 reactions or something like this, but 120 is just, and it doesn't seem to have that much of an effect for this kind of simple cases, the chemistry. Then when you go turbulent and things like this, is again different. Yeah.
Quick one following the last point.
Yes. Oops.
Acoustic glass.
Yes.
What kind of glass?
Well, okay, I imagine putting changing slightly the boundary condition at the end, adding some impedance there, instead of being perfectly reflecting walls.
So, in the framework you've chosen for the simulation, is it easy to do? Or?
Yeah, I change R from 1 to something with a complex value.
Any complex value could be.
Yeah, well, because the calculation is for the acoustic is really there's nothing in some sense. It's just really that's this, okay. And so here I obtain this boundary condition because I impose some particular. Your R is 1, R is -1. That comes up from that. If I got something different, then I will get something different here. And I don't see why it wouldn't go through.
But this is also true because you're considering pure frequency situations.
No?
No, I mean, that's, yeah, maybe this is something like this. It locks on the fundamental.
Yeah, it finds it by itself because I work in time space. It finds the fundamental frequency by itself.
So you're saying it's a perfect case because
yes.
In the real world,
okay.
you would have spectral contents.
Yes, that's true.
LCs
Yeah. No, you're right. And also in the real world, as far as this. What do you mean by frequency when your flame is propagating in a duct? Even the characteristic frequency changes continuously with the. So sometimes when people talk about frequency of combustion instability, I mean in that case, for example, it doesn't really make sense to look at the frequency. You can say, oh, it's roughly this because it varies between what it is there and what it is there. So. No.
Okay,
Thanks.